On July 1st, 2025, astronomers caught a flash of the impossible. An object from another star system, moving at 60 kilometers per second, shrouded in a veil of carbon dioxide unlike anything seen before. Scientists named it 3I/Atlas. But nothing about this so-called comet fits the rules. Its chemistry defies every model, its origins can't be traced, and its true form is hidden behind a mask thick enough to stop the James Webb Space Telescope. Now, a bold claim rips through the scientific world. Could 3I/Atlas be alien? This isn't just a weird rock. If these anomalies mean what some astrophysicists suspect, our place in the universe is about to change. But what exactly are they hiding? And what happens if we're right? On the night of July 1st, 2025, the Atlas telescope in Chile tracked a faint streak against the crowded backdrop of the galactic center. The system, designed to scan for asteroids that might threaten Earth, instead caught something wholly unexpected: a visitor from the deep beyond. Within hours, automated alerts rippled through the astronomical community. Initial calculations revealed a trajectory with an eccentricity of 6.14, far outside the bounds of any object born in our solar system. This wasn't a remnant of familiar planetary debris. It was the third confirmed interstellar object ever detected, following Oumuamua in 2017 and Borisov in 2019. The Atlas team quickly realized the scale of what they had found. Early data suggested a body up to 20 kilometers across, dwarfing Oumuamua's estimated 400 meters. Traveling at 60 kilometers per second, over 130,000 miles an hour, 3I/Atlas was not just fast. It was ancient, carrying the kinetic memory of a journey measured in billions of years. Its passage through the solar system would be brief, its path carved by gravitational encounters with stars and nebulae long vanished from the sky. Survey telescopes in Hawaii, South Africa, and Spain joined the hunt, retracing the object's earliest glimmers in archived images. Each new data point refined its hyperbolic arc, confirming it was not bound to the sun and would never return. The object's velocity and angle implied origins in the thick disk of the galaxy, a stellar population older than the sun itself. For astronomers, this was not just another icy wanderer. Expectations ran toward a classic comet: rock, ice, perhaps a faint tail. But as spectra began to arrive, the object's true nature slipped further from established models. The numbers, the speed, the sheer improbability of its arrival all pointed to a cosmic messenger unlike any seen before. The world's most powerful telescopes prepared to probe deeper, chasing a mystery that had just begun to unfold. The James Webb Space Telescope turned its gaze toward 3I/Atlas in August 2025, capturing a spectrum that rewrote the rules of cometary chemistry. Instead of the expected signature, a balance of water vapor and carbon monoxide, Webb's detectors recorded a staggering excess of carbon dioxide. The data showed a carbon dioxide to water ratio of 8:1, the highest ever measured in a comet, and a full 16 times higher than what models predict for bodies at this distance from the sun. For context, most comets in our solar system exhibit a carbon dioxide to water ratio below 1, with only rare outliers like C/2016 R2 even approaching such extremes. Here, every kilogram of water vapor escaping the nucleus was dwarfed by 8 kilograms of carbon dioxide, an abundance so far outside the norm that it sits more than 6 standard deviations above the typical trend. Martin Cordiner, principal investigator for the Webb campaign, described the data as both spectacular and baffling. In just 10 minutes of observing time, the telescope revealed a chemical profile that defies every established model of cometary formation. The coma, Webb's term for the shroud of gas and dust enveloping the nucleus, was dominated by carbon dioxide with water, carbon monoxide, and carbonyl sulfide trailing far behind. The numbers left planetary scientists without a ready explanation. No known process in our solar system can account for this kind of chemistry. The Webb team's findings forced astronomers to confront a paradox. 3. I/Atlas does not fit into any existing category. Its chemistry is not just unusual, it is, by all current understanding, impossible. The question then becomes, what kind of environment could produce such an object? Or what processes could have altered it so completely during its journey through interstellar space? The challenge now lies in deciphering whether this thick carbon dioxide veil is a natural byproduct of an alien birthplace or something more deliberate, an enigma that only deepens as the coma itself blocks any direct view of what lies beneath. A thick veil of carbon dioxide envelops 3I/Atlas, stretching outward as a diffuse shroud that dominates every observation. This coma, rich in carbon dioxide and laced with fine dust, forms a luminous envelope that outshines the nucleus by orders of magnitude. Spectroscopists aiming the world's most advanced telescopes at the heart of the comet find themselves staring into a haze, one that, despite its brightness, remains optically thin. The nucleus itself, likely no more than a few kilometers across, is lost in the glare, its direct light drowned out by the surrounding cloud of gas and dust. Even the sharp eyes of the Hubble Space Telescope can trace only the faintest hint of a solid core, setting upper limits on its size but revealing no clear surface or structure. In the infrared, the problem deepens. The James Webb Space Telescope maps the coma's carbon dioxide emission, revealing a plume that fans sunward, but the central object remains frustratingly invisible. The veil does not block light in the way of a wall or a curtain. Instead, it overwhelms, scattering and re-emitting energy until the nucleus is buried beneath a wash of radiance. The result is a kind of cosmic camouflage, one not of opacity but of brilliance, where the true form of the comet is hidden by the very activity that makes it remarkable. For comet spectroscopists, the frustration is acute. Every attempt to pierce the shroud yields only more detail about the coma itself, never the object it conceals. The question lingers: is this veil a natural consequence of exotic chemistry, or does it serve a deeper purpose, masking something that was never meant to be seen? Avi Loeb, the Harvard astrophysicist known for challenging orthodoxy, has placed 3I/Atlas under a microscope of radical possibility. Loeb's analysis doesn't dwell on chemistry alone. He turns to the object's path, a trajectory so stable, so precisely aligned with the ecliptic, that he calculates its odds of occurring by chance at just 0.005%. For Loeb, this is not a trivial coincidence. The comet's retrograde orbit, nearly flat to the plane of the solar system, allows it to pass close to Venus, Mars, and Jupiter in a single sweep. Such encounters, he argues, could be a sign of intentional navigation, an engineered path rather than a random wanderer's luck. The size of Atlas, too, stands out. At up to 20 kilometers wide, it dwarfs previous interstellar visitors, pushing the bounds of what natural models predict should survive the trip between stars. Loeb points to the object's unwavering course and its fortuitous planetary flybys as evidence that it might be more than just a comet. In his view, the possibility must be considered. Could Atlas be a probe drifting silently through the solar system, its true purpose hidden by design? The mainstream response is swift and skeptical, but Loeb's argument remains: when the statistics defy expectation, the door to the extraordinary stands ajar. NASA's Planetary Science Division addresses the puzzle of 3I/Atlas with a model grounded in the chemistry of distant star systems. Their astrochemists suggest that the comet's extreme carbon dioxide abundance could be the natural result of formation near a carbon dioxide ice line, an invisible boundary in a protoplanetary disk where temperatures drop low enough for carbon dioxide to freeze out of the gas phase. In disks surrounding other stars, this line can sit far from the warmth of the parent sun, allowing icy bodies to accumulate more carbon dioxide, than anything seen in our solar system. Over billions of years, cosmic rays and high-energy particles bombard these ices, driving chemical reactions that further alter the original mix. Laboratory simulations show that radiation can convert carbon monoxide and water into new carbon dioxide, gradually reshaping the comet's inventory as it drifts through interstellar space. NASA researchers point to these processes as plausible explanations for the 8:1 carbon dioxide to water ratio measured by the James Webb Space Telescope, arguing that such chemistry, while rare, fits within the spectrum of what nature can produce. Even so, they acknowledge that 3I/Atlas stands at the edge of known cometary diversity, pressing the limits of current models. The agency's stance remains clear. Until direct evidence proves otherwise, the object is considered a product of natural astrophysical processes, shaped by an environment far removed from our own. ESO spectroscopists tracking 3I/Atlas as it moved inward past 4 astronomical units began to catalogue a series of findings that defy easy explanation. Nickel emission lines, normally paired with iron in every known comet, appeared alone. 22 distinct transitions mapped in the ultraviolet, but no iron detected at any wavelength. This decoupling of metals has never been observed, hinting at chemical or physical processes that have no precedent in solar system science. Cyanide, a classic marker of cometary activity, registered only faintly at first, then surged past detection thresholds as the comet drew closer, its production rate rising by orders of magnitude in a matter of weeks. Yet the usual family of daughter molecules, C2, C3, NH2, remained stubbornly absent, as if Atlas were following its own private recipe for cometary chemistry. The coma's brightness profile, mapped in detail by Hubble and Webb, revealed a forward-facing plume that glowed not just from reflected sunlight, but from active outgassing, its direction locked to the Sun-comet axis. At distances where most comets lie dormant, Atlas was already awake, its activity measured as early as 6.4 astronomical units, far beyond the frost line, long before water ice should sublimate. Each new observation, from nickel-only emission to distant activation, deepened the puzzle. With perihelion approaching and the comet's window for study closing, astronomers faced a mounting sense of urgency. Every spectrum, every light curve might be the last chance to decode a messenger that refuses to fit any known pattern. 3I/Atlas was discovered on July 1, 2025 by the Atlas Survey, marking it as only the third confirmed interstellar object ever observed. The James Webb Space Telescope measured a carbon dioxide to water ratio at least 16 times higher than any known comet, a finding for which no current solar system models can account. Astronomers have documented a dense carbon dioxide veil obscuring the core, along with signs of nickel-rich emissions and unexplained activity far from the Sun. While Harvard astrophysicist Avi Loeb points to these anomalies as possible evidence of artificial origins, NASA and other institutions still argue for exotic but natural explanations. Yet, as of now, the true nature of 3I/Atlas remains unresolved. With perihelion approaching in late 2025, scientists have a limited window to gather more data before this object leaves our reach forever. The facts are clear. Every new observation deepens the mystery and challenges our understanding of what can arrive from the stars.